Okay, ji, Bismillahirrahmanirrahim. Let's start with the new topic of non-deterministic finite automata. So previously we studied finite automata, and this is another type of finite automata which is non-deterministic. So the first thing that it should be very much similar to already studied finite automata, but there are some relaxed rule that you have to consider. And those relaxed rules are related to the outer degree of the states. Um, and the second thing is the non-deterministic finite automata NFA that we will study will accept exactly the same language as your FAs were doing in previous lectures. So these are the two things that you have to keep in your mind. For example, here, uh, this is on the left hand side, you are seeing if FA, and on the right hand side, you are seeing a NFA. So these FA, this FA and NFA is for this language 11 comma 110 whole star, and then there is a zero at the end of the strings that will produce from this expression. So as you are seeing, this is the initial state, and if 1 1, so if 1 1 will come out from this expression and 0 at the end, then 1 1 and then 0, it is accepted. And if this one will come out 1 1 0 and then 0, so 1 1 0 and then this 0, so here it is again accepted. Or only 0, so from initial state only 0 is also accepted, and the rest of the states and transitions are just to uh, fulfill all other requirements. But these are some basic requirements that are the compulsory part of this FA on the left hand side. And on the right hand side, we have an NFA, an example of an NFA. So this is the start state Q0, and you should have to focus first on the minimum string 1 1 and then 0 at the end. So 1 and then 1 and then 0, and we will reach at Q4, which is the acceptance state. So 1 1 0 is accepted here. Now take the other one, 1 1 0 and then 0 at the end. So 1 1 and then 0 and then again 0, and we will again reach at Q4, which is an acceptance state. So, and simple thing is, when it will be null, only 0. So from Q0 we can take a 0 and we can reach on Q4. So all the strings which are acceptable here are also acceptable here in on this NFA. But you can see that from Q0 we are taking 1 as an output, and then from Q0 we are again taking 1 as an output, but to the other states. So here 1 is going towards Q1, but here an edge or arrow with label 1 is going to another state Q2. So this is something different from the FA that you studied in previous lectures. So, and there is another output, which is the third one with label 0 and going to Q4. So this state has 3 outer degree, which is different from the FA. If my input symbol is containing only 2 symbols, then according to the definition of FA, every state must have 2 outputs. But here in NFA we have 3 on this initial condition. So in NFA we can have different outer output degree or outer degree on the states. It is possible, and it is legal in case of NFA. And this is an NFA, and it is accepting the same language as this FA is on the left hand side. So both of these statements which are mentioned here in the beginning of this lecture are you can check on these FA and NFAs. Now move on to some other uh, heading which is related to this NFA. So what is the difference between this FA and NFA? So for some states, there are not transitions for both input symbols. So it is also possible in case of NFA that we don't have any transition or we don't have any edge going out from any state in case of NFA. So this is possible in NFA. For example, Q4 here. So for example, this is Q4 and you are saying there is no outer degree here. So it is also possible in case of NFA. So there is a kind of freedom in NFA. So it is, you can say, much simpler than this design of FA. Number two, there is more than one arrow corresponding to same input, e.g. Q0 for input 1. So if you see, so Q0, so input is 1 going out, input is 1 going out. So it is, we already discussed this point, but it is something different from the FA, and we have two outputs for the same input symbols which is different from the FA. So that's why it is mentioned difference from the FA. Now move on to the definition of an NFA. So an NFA is a 5 tuple, again with very much similar to your definition of FA. 5 tuple machine M with the Q set of states, sigma and set of input symbols, Q0 initial state, is accepting states, and delta is the transition. So Q and sigma are non-empty finite sets. We know there are some states in Q and we know there should be some input symbols in sigma. So that's why it is non-empty and it is a finite sets. And Q0 is also the state from the set of bigger Q, and A, which is for acceptance states, is also a subset of this big Q, which is a set of states. And the delta, we can write the delta, which is the transition function. So delta can be written for the case of an NFA like this: delta colon Q cross sigma uh, equal to 2 raised power Q. For the here, Q cross sigma means you can take any state from the set of states and you can take any symbol from the set of symbols, and uh, after applying that symbol or after applying that input on that state, you can reach at some other states. And if you write the complete set of states on the one column and the complete set of input symbols on another column, and if you apply the Cartesian product, which means all combinations, then definitely you will reach at some states which will again be the part of your set of states. So the total combinations, the all total combination after applying the Cartesian product between Q and sigma would be 2 raised power Q. 2 and raised power the number of states in that NFA. For example, in that NFA, if the number of states is 3, then 2 raised power 3, you should have 2 multiplied by 2, and then 2, you should have 8 uh, arrows or labels, you can say. So possible transitions, edges. So 2 raised power Q is basically the formula which is giving you the total number of transitions available for that FA. And here, okay, move on. Q is the set of states. We know sigma is the alphabet set. We know that Q0 is the initial state and A is the set of accepting states. Set of accepting states, plural, because more than one accepting state is possible, just like previous definition of FA and also the NFA. Now, non-recursive definition of delta star for NFA. Non-recursive. When it is a non-recursive, then it means we have to explain only deltas, single transition function. So it is a very much theoretical stuff. So we will read this stuff and then we will try to understand this stuff. So for example, if X, just look on the screen because I am highlighting the cursor and then you will understand. So maybe I can also use the annotation. So if X if x is equal to a1 and so a2 and so on an, so if x is a string and it contains alphabets, for example a1 a2 and so on an, then saying m can be in state q after processing x. Now you have to suppose that you have processed this string x, which is containing alphabets from a1 to an, and after processing that string x by this machine m, then we can think that that machine will approach at some state and we can call that state q. So if this is the situation, so x is a string which is containing alphabets and m is a machine. After processing that string, m machine will reach at some state and we are calling that state q. In other words, means that there are state p0, p1 and so on pn, so that p0 is p, so this is p0 is, we are calling this p0 is p and we are calling this pnq. So we are now taking this example, and then we are comparing this example to our previous one. In previous discussion of this, when the string was x, after processing x we were reaching at q. But suppose if the alphabets would be from p0 to pn, and p0 is something, after processing p0 we are reaching at state p. Here p means we are reaching at some state p, and after processing this pn, which is an, we are reaching at state q, which is very much similar to this q which we are already discussed. And if this is the situation, then we can also, so we have seen the case of x with alphabets from a1 to an, and now we are making another, uh, after processing after processing a1, we are supposing that we are reaching at p0. After processing a2, we are supposing that we are reaching at p o, um, uh, p2. After processing a3, we are reaching at p3 and so on. And after processing an, we are reaching at state q, for example. So we are just taking another example and we are relating that example simply. So from our previous discussion, as p0 is something, we have taken this p0 is something equal to p. So if p0 are p, we have supposed this thing here. We are supposing that p0 is equal to p. So we can reach from this state p0 rp to p1 if we process a1. After processing this alphabet a1, we can reach at p0, which is a p according to our this supposition, and then we will reach at p0 after processing a1. And after processing a2, we will reach from p1 to p2 and so on. After processing an, we will reach at pn. From where? From pn minus 1. And we also call that pn is something, a state which is q from the supposition here. We have supposed these things here. We are basically now giving labels to each and every state after processing the string x. And this is individually, this is something delta, this is another delta, this is another delta, because we are discussing each and every transaction, we are discussing each and every delta, because we are considering non-recursive definitions for an nfa when we process some string x as mentioned here. which is containing some symbols. So now I am clearing this drawing and then I am moving forward. So we have seen that from state Pn minus 1, we can reach on Pn, which is a Q, but this is something after processing An. So another way to say something, a simple way to say M can get from Pi minus 1 to Pi. So from this previous discussion, we can say that we can reach from previous state Pi minus 1 to next state Pi by processing Ai. So if we replace these numbers with some variable I, then what will be the formula? This is something Pi minus 1, this is Pi, and this is again Ai. So that is written here. From Pi minus 1 to Pi by processing Ai. And now this theoretical stuff, you can sum up this theoretical stuff into the form of an equation like this. And what is this thing? So pi is some state we have reached, like this one. So pi is what? Pi is some state, for example this state Pi. So Pi belongs to, so suppose you have reached at Pi, then from where you have reached on this state, the answer is after applying different transitions. So that's why we can write it as Pi belongs to delta, which is a transition. And how we reached here at Pi? From previous state Pi minus 1 comma Ai. So on previous state Pi minus 1, after applying the transition with Ai, we can reach at Pi. And here for each I with, and here you can just explain what your I is, and our I is greater than or equal to 1 and less than or equal to n from this previous discussion. From this previous discussion, this is P1, P2, and so on Pn. So I is greater than or equal to 1 to n. Maybe some person can think that where is this zero? We are not considering this zero because this is a state where we normally reach. And for example, from P0 to P1, so we are reaching at P1, and then we are reaching at P2, and then P3, and so on Pn. So that's why our states starts from P1, P2, P3, and so on, which you can write here. That's why our I is greater than or equal to 1 and less than or equal to 0. Now I am moving forward. So now this equation is explaining this whole theoretical stuff that we have studied up to this point. So now this equation is something you can understand that what this equation is saying, what this equation is containing, the story. So now moving forward, we can say that now maybe we have to form some other different equation. So we can also say that Pn belongs to, now you can change this I into n. So Pn belongs to, how we can reach at this state Pn? We can reach at this state Pn after applying multiple transitions. Here it is only delta one single transition. From previous state we can apply Ai, and then we can reach Ai. But this is Pn. We can also mention this thing in a to represent all our transitions from the initial states. Now we are going to finalize our equation from initial state to the final state of the machine M, which is an Nfa. So how we can reach at state Pn? We can write it as, said delta star means multiple transitions, more than one transition, and we can reach at this state Pn from the initial state P0, but the string should be A1, A2, and so on An. So first we will process A1 at P0, then we will reach at state P1, and then from P1 to P2, but after applying this A2, the same story as you have seen here. So now at P0, if we have a string like this containing the alphabets, then after applying multiple transition, we can reach at this Pn. So this is something now, this equation is concluding the whole story that we have seen here. Um, and again, for I greater than or equal to 1, if we convert again, if we convert this equation again into the form of I, then we can write it as I is greater than or equal to 1, and then we can write Pi is equal to delta star pre0 a1 a2, and we can convert this n into ai. So this equation is also saying the same thing as this equation with the notation Pn. And I hope that you now have the understanding. Now moving on to now a little bit complex form. The first one is non-recursive definition of Nfa. If I ask discuss the non-recursive definition of Nfa, then this is the thing that you have to explain and you have to reach at this equation. And now the recursive definition of delta star, recursive definition of transitions which are involved in in NEFA or NFA. So now we have to again suppose something, and then we have to reach at the equation, something like that, like this. For example, this is the form of equation. So suppose or let I is n minus 1, which means previous state. I is n minus 1, not n, not an or not pn. So I is n minus 1. And our string y is from a1, a2, and a minus 1. And our string is one step behind. Then from our previous discussion, we can write from our previous equation, this one, these two ones, we can write Pn minus 1 belongs to delta star, which means multiple transition. And this is P0, which is P. We have said that our P0 is P here. We have said this thing here. So don't worry if you have the similar things. You have to remind these things in your mind that my P0 is also a P, because now we are going to generalize the equation. So delta star is delta star. This is P, which is P0, and I have this string Y, A1, A2, and so on. Minus. Here I have written Y not in capital letters but small letter, but I am mentioning the same string. So I am mentioning the same string. I can annotate if you want. I am mentioning the same string. The same string. And okay, so at P0 or P, after processing this string, I can reach at Pn minus 1. And then similarly, I can reach the final thing with Pn belongs to, what is my Pn? Pn is the last one. So what I have to do, only one transition from Pn minus 1, from Pn minus 1, which is this thing, and I have to process only the one alphabet, which is an, then I can reach on this state Pn. Okay, up to this point, this is something fine according to our previous knowledge. There is no any complex thing up to this point. I can clear the drawings. Now we have to explain our story, or in other words, now our in other words, or we have to rephrase our story. In other words, if q is what? Q is a state. Anyhow, in other words, if q belongs to delta star and then p comma yn, so p is my p0 or initial state, and y is a string one step behind up to the second last point, and then an is the last input symbol that I have to process, and where I can reach at q. And q is what? According to my previous discussion, I have said that this my q is my pn. or Q is any state where I want to reach. In other words, if Q belongs to delta star P comma Yn, that's clear, then this is something from my previous knowledge. That is fine. Then there is a state R, and R is some previous state which is Pn minus 1. This Q is my Pn actually. Then I have a state R, and I am saying that R is the previous state Pn minus 1 in the set. Then in the set delta star P comma Y. So if I starts from P0 or P with string Y, which is with n minus 1 at the end, where I will reach at Pn minus 1. So we can, I am now saying that I am reaching at Pn minus 1, but I am saying that okay, so now I am taking another name for Pn minus 1, and that name is R, nothing different. So you can consider Pn minus 1 as if with a new name R. So that's why I can say then there is a state R is equal to Pn minus 1 in the set. And how can I reach on that state? Same story, delta star, and from initial state P, and then applying with the processing with this string Y, which is this one, Y is equal to A1 to AN minus 1. And then I am sure that you will understand that after processing this whole alphabets, where I will reach at Pn minus 1, which is R. So I am saying that I can reach at R by processing this thing. Okay. So then Q belongs to, and then Q is my final state, and then Q belongs final state, not in that terms of with acceptance, set of acceptance. No, I am Q is something where I want to reach actually. So then Q belongs to delta, and R is my Pn minus 1, and at Pn minus 1 or at R I can apply the last input symbol An. Then I can, and this is only one transition, so that's why it's only delta, and then I can reach at some state Q, which is my Pn. I have said this thing here, Pn is equal to Q. So this is the drawback of online classes. If it will be the physical, then you can understand that on the whiteboard we can explain these things with great confidence. But now you have to anyhow maybe a little bit uh, lagging behind in understanding maybe. So you have to bear these things because I don't have those resources. So we have to live with these situations. So then Q belongs to, and how can I reach at Q? So I can reach at this state Q, which is Pn. Currently I am at state R, and after processing this last input alphabet symbol An, and this is one transition, and then I can reach at Q. This is perfect. This is fine up to this point. Now, again, what is next? This is the story from this point, this line to that line. So now we have to discuss the same story in reverse direction. And how can we do that? If we consider it in reverse order, then we can say, this is my last point in previous discussion, Q belongs to delta R comma An. Then we can say that if Q belongs to delta R An, this is the thing that we have studied here. So if Q belongs to delta R comma An for some R, and how I reached at R, this is my P initial state, and this is my string Y with An minus 1 at the end, and after applying multiple transitions over it, I can reach at R. Then we conclude that Q belongs to delta star. Now I can write this, how I will reach on this Q at from initial state P after processing this Y, and then at the end N, and after applying multiple transition, because I am writing the whole thing cumulatively, so that's why it's a star here. then I can reach at q. This is also fine, nothing difficult here. Now can finalize my recursive formula, because I am now discussing recursive definition of delta star for an Nfa. So now my recursive formula would be like this: delta star from initial state p after processing some string y without an, but an is at the end now. So I can reach at some state q such that q belongs to transition delta r comma an. This is the previous state r, and after applying an, I can, this is single transition, I can reach at q for some r. And now I am explaining or opening this r. So this is something from previous state to this state q. But what is this r? For some r, r belongs to delta star p comma y. P is initial state, y is that string containing a1, a2, and so on, an minus 1. So that is something we have already studied in previous steps. So now this is the recursive formula for reaching at state q. Or I can also rewrite this equation as delta star p comma yn, same thing, or I in union form. So delta or is the previous state, and after applying an, definitely I will reach at q. But what is my r? My r is the transitions from my initial state to pn minus 1, to the second last state. And how can I depict here in this equation? I can say, okay, del one transition for initial state union, one transition for second state union, one transition for third state, one transition for fourth state, and so on. And then I can conclude union for the last pn minus 1. So in this way I can explain my r actually, so which is here. So union big U with r belongs to multiple transition from my initial state p, and after processing this string y, which is from a1, a2, and an minus 1. So after applying these multiple transitions and taking unions of those transitions, and then I will have the r, which I can apply here, and then after applying an, and after applying the single transition only, then I can get something on the right hand side which should be equal to the thing on the right hand side, which is reaching at state p and rq. So this equation is also okay. So finally we can say that now we are concluding that for any state q which is from the set of big Q, if we have a null on that state, where I will reach at this, I can reach at the same state. This is one option. So q, if I have a state q, any state as mentioned here, and if I have a input symbol null, I can apply multiple transition, depends on where. For example, if in an FA, if I am getting null, I can reach on multiple transitions ahead. So where I will reach at some state q, and it could be any according to this definition. So in an FA, by taking null, I can reach at any state. Now, number 2, for sorry, for any q means any state. Here, for any q belongs to big Q, and y, which is my previous string from a1, a2, and so on, an minus 1, and that string belongs to sigma star, fine. And this is the last symbol, a belongs to sigma, and this a is something an. So I can write this from q comma y is my string containing a1, a2, a3, and so on, an minus 1, and then last symbol a. I can reach, after applying multiple transition, I can reach at some state something, I can say Q according to my previous formula, but I can reach at some state, and how that state can be achieved, I have to open this up on the right hand side. So this is again the rewriting style of these equations. So delta r comma a, r is something my previous state. After processing this a, which is a n, I can reach at the state where I want to reach. And then here I am explaining or opening up or explaining what this r is. So union r belongs to delta star q comma y. So here q is my this state q, it can be my starting state. So at starting state, after processing this y string, multiple transitions and taking unions, I can reach at some state r, after which I can apply this a, and then I can reach my wanted state, which is Pn, you can say. So these 2 points are okay, nothing is wrong with that. And this is your recursive uh, definition for the NFA. You should have to keep, either you can keep this equation or keep the understanding of this equation in your mind, or you can keep these 2 points in your mind. It's up to you. Now the definition, acceptance of an NFA. So in previous lectures, we have seen the definition, acceptance definition of FA, and now we are going to see the acceptance definition of an NFA. The definition is same. You can just repeat that definition for the NFA, because we have to clear what is meant by acceptance of an NFA. So you should have to give your sentences or statements in this regard. So suppose if we have an M containing these 5 tuples, and this is an NFA, N is right because you can say N, sound is with a N, not exactly N, but N starting with A. Anyhow, Bn NFA, the string X belongs to sigma star if we have a NFA M, and if we have a string X, and if this string is accepted by M, this string is accepted by M if delta star from initial state Q0 and this X, if we process this string X, and after applying multiple transition, then we will reach at some state. That state can be Pn, or that state can be Q. Intersection set of acceptance states. So I have some states here, and intersection set of states, set of final states, set of accepted states, you can say. So this A is the set of final states for this NFA. So on the right hand side of this intersection operation, we have the set of final states, and here on the left hand side of the intersection operator, we have a state where we have reached, and now we are taking intersection. If that intersection is empty, then it means we have not reached at the final state yet. But if that intersection is not empty, then it means that we are at the final state. Hopefully most of the students have this understanding, because this is intersection with the state, and here on the right hand side we have the set of final states, and we are taking intersection, which means that the final state must be the part of the resultant set. So if that set is not equal to an empty set, then it means we are at the final state of this NFA, and then it means that the string is accepted. So this is acceptance of an NFA. So, and in this way, And we have taken this string X a very much general string, so which means that all possible legal valid strings. So now we are saying the language recognized or accepted by M is the set language of M. So if some language from which these kinds of strings like X is producing, if that language is accepted by that M or recognized by that NFA M, then we can represent in mathematical form that set as L of M of all strings accepted by M. Now, another sentence, for any language, for any language, now we are taking any language, L, which is a subset of sigma star, we can say that language, we can say this language or that language L is recognized or accepted by M if that language L is equal to L of M, which we already said that L of M is a language accepted by M. So this language L should be equal to L of M, should be equal for should be equal to the set of languages of this NFA, you can say. And then here in this theoretical stuff, first we are explaining the acceptance of NFA in terms of a string. Then we are explaining the acceptance of NFA in terms of a language. And we are representing these sentences as you are seeing on the screen, nothing else. You can write these statements in your own words. This is not a big issue. And here we have an example, and this is an example explaining the recursive definition of NFA. This is an example for the recursive definition. Using the recursive definition of NFA, we are basically explaining that how an NFA can accept a string or not. We are executing some strings over some NFA here in this example, and then we are showing the process of those strings in the form of this equation that we have studied here. So for example, M is Q sigma Q0 A delta, where this is now my NFA. So starting state Q0, initial state Q, if 0 or 1 will come, this is the loop here. I am reaching at Q0. If 1 will come, I can also reach at Q1. If 0, 1 will come, I can reach at Q2. 0, 1 will come, I can reach at Q3, which is an acceptance state. So only Q3 is acceptance state here. So now we can read the things here. So now my Q is Q0, Q1, Q3, Q2, and Q3 here. Q0, Q1, Q2, Q3. Sigma is only 0, 1. Acceptance states is only Q3, and delta is given by the following table. So this is my transition table, and my all deltas are mentioned here. So here I am mentioning this Q is for states, and states are Q0, Q1, Q2, 3. You can write these states here. And then the first transition from any state Q with the 0 input symbol, transition from any state Q with input symbol 1. So because there are 2 input symbols. So this transition symbol is according to the input symbols, but those input symbols are mentioned in column direction. So Q0, I am here with the 0. By taking 0 at Q0, where I can reach at Q0, you have to mention it here. And at Q0, after taking 1, where I can reach at Q0 or at Q1. So I have mentioned this thing here. At Q1 with 0, where I can reach, Q2 mentioned. Q1 with 1, where I can reach, Q2 mentioned. Q2 0, Q3 and Q2 with 1 I can reach at Q3 mentioned. At Q3 with 0 or 1 I don't have an output degree here, so that's why it's a null null. Now, so this is just, we have not studied uh, the example for different strings yet. So now we have to determine the language recognized by the machine. So now we can say that what kind of language is recognized, or what kind of different strings can be recognized by this NFA or by a machine. We can conclude this from the table, this table. And now we are taking first example. So we are checking delta star Q0 and with 0. Where we will reach, I have to write these things in mathematical form, in notations, as we have seen previously the recursive definition of Nfa. So Q0 and 0, Q0 and 0, where I'm reaching Q0. So that's why Q0 is mentioned. And delta star Q0 with 1 and multiple transitions. Q0 with 1. Here Q0 with 1, multiple transitions are Q0 and Q1. Multiple transitions are already mentioned in this table. So I don't have to look here in this diagram. I can simply look into this table and then I can conclude what are the states Q0 and Q1. So Q0 and Q1, it is mentioned. So we have not reached at the acceptance states yet by taking 0 or by taking 1. So now from recursive transition concept delta star with some other string. Delta star, this is one input symbol. So that's why we have not reached at the acceptance acceptance states yet according to this NFA. So that means that some multiple input symbols are required, which means that I have to apply the multiple transitions, which means that the recursive definitions are involved. So delta star, so delta star Q011. So I am now taking this string. These are the random string. You can take your own strings. So this is not something fixed strings. You can take your own strings, not issue. So delta star Q011. So initial state and then 11. And according to my previous definition, recursive definition, this one, this is R previous level and this is the last symbol. I have to now write, this is union R belongs to sigma star P comma Y. So I have to now mention this thing into that format. So here I'm mentioning, okay, delta, this is my R, which is the previous state. And then after applying this last, and maybe I have to and use annotation. So this last one, I have mentioned this last one here. So from previous state Pn minus 1, which I am calling it R, and after applying this last symbol 1, where I can reach at some wanted state. So this is, that's why it is delta. This is only one transition. But what are the previous transitions? That is something you have to show in this union. So that's why R belongs to delta star from this initial state Q0, and then only one was remaining that I have to write it here. This one is that one. And after applying multiple, here I have only one symbol, that's okay, but if it would be more than one, then it is delta star. So after from initial state and after processing and taking union, I will reach at state R, and then after at R I can apply this one, and then I can reach at the final state. So now I'm clearing again. So now the next, here delta R comma 1 is the same thing, and this union, now I have to write the states according to this diagram or this table. So union R belongs to from Q0 to 1. What are the state Q0 to 1? From Q0 to 1, these are the two states Q0, Q1, and something I already have done for delta star Q0 to 1, Q0, Q1. So I can either refer to this calculation or from the table. So R belongs to, R is something belongs to delta star Q01 is Q0, Q1. So these two states, Q0, Q1, are the multiple transitions, are the set of states which is belonging to this R. So I can write, this thing here. I can replace this thing here with that one according to my this calculation. Okay. Now I have to open this up further. So now I am opening this up further. So Q0, so delta, so I what was my symbol? 1. So now Q0 Q1 is something approaching to R, and this is 1. Now apply this. So this is R, which is this one, and this one is remaining, which I have to apply actually. So that's why Q0 and 1 here it is mentioned delta Q0 comma 1. There is no star here. And union, this is union, and Q1 here and 1. Q1 and this 1. So delta Q1 comma 1. And then again from Q0 and 1, what are the states? What are the states? Q0 and 1, what are the states? From Q01 I can see in the table, and this is again same, either from here Q01 or from here Q0 and 1. This is delta is mentioned here, delta Q0 Q1. So Q0 Q1, so Q0 is Q1 is this thing, and then at Q1 and input symbol 1 where I will reach, you can see it from the table Q1 and then 1. This is Q2 only. So Q1 and 1, this is Q2. And now take the union again. This is Q0, Q1, Q2. So this is now our final set of states. So I am reaching at Q2 basically. So after applying 1 1 at Q0, where you will reach, I will reach at Q2. And from where I will reach, first I will reach Q0, then I will reach Q1, and then I will reach Q2 after applying 1 1, which you can also check on this diagram. From Q0 1, and then from 1, this is I am reaching at Q2. And now I am taking you can study this example by yourself, and I am reading this part because it is approaching at Q3 with this example 111. So delta star Q0 111. So how can I write it as according to recursive formula? Delta R comma 1. This is last one, and some two ones, double ones are remaining. So I can write union R belongs to delta star, this Q0 and this double one here. Okay, now open it up. Delta Q011. This is something you have already calculated. Q011 delta star. What are the states? Q0, Q1, Q2. So you can refer it. You can just give a label for this equation, like this is equation 1, and then you can write something using equation 1, and you can write all the things here. So I have three states now: Q0, Q1, Q2. So I can write those states now in open form. I can skip all these steps. I have this state, I have these states Q0, Q1, Q2 here. I have these, and I can apply this one over these three states, Q0, Q1, and Q3. That's why delta Q0 comma 1 union delta, uh, second one is Q1, I think. Yes, Q1. Q1 and 1 and union Q2 into 1. So these Q0, Q1, and Q2 is something I am getting from here, which is an example of Q0 with 1, 1. So, okay. And from Q0, after applying 1 at Q0, I know that I can reach at Q0 and Q1. So you can write all those things as, and then you can sum it up. But I have skipped many steps here. And then I am writing this thing Q0. Okay, from Q1 after applying 1, I can reach at Q2. But at Q2 after applying 1, I can reach at Q3. So that's why Q0, Q1, Q2, and Q3 are mentioned. This Q3 is acceptance state. So now I can say this string triple one is the string of a language that is accepted, that is accepted by this NFA. So this is an example for the clearance or for the representation of acceptance of an NFA. Okay. This is with triple one, and this is what 011, and here I am not reaching at Q3. So, and then we can say we have seen that triple one is accepted but 011 is not. So the language of M is, now you can conclude the language. You can also conclude the language from by looking at this stuff. This is 01 star, and then this is 1, and that's 0101, which means 0 comma 1 power 2. So 01 whole star, 0 comma 1 whole star, then only 1 in between, and then you can write 0 comma 1 raised power 2. That is the expression from this diagram. So you can so the language of M is 0 comma 1 whole star, 1, and 0 comma 1 raised power 2. So this is the regular expression for this NFA. So this is basically a theoretical discussion. It has different dimensions and directions according to the strings that you will use. And finally, you have to present the regular expression that this is the language of the RFA. And that is again something, now you have enough practice and you can write the regular expression of this NFA by looking over it. But again, if I am asking to give an example to explain the acceptance of an NFA by using some example, then you have to draw some NFA, then you have to draw this transition table, and then you have to check some strings over it, and then after presenting some strings you can finally conclude, okay, that this is the regular expression, and this is and the languages that will be produced from this regular expression would be the language of that NFA. So in this way you can conclude this topic. So anyhow, you can also see this stuff here. Now I am moving towards the actual beginning topic of this NFA, which is a conversion of an NFA. So this is A is mentioned here. Okay, leave it. Grammatical errors there, so leave it. So conversion of an NFA to FA using subset construction method. So now we are going to study the subset construction method, and this is a method through which you can convert an NFA into a FA. So how we can do this, let's have a look over it. So this is the NFA which is given to us, which is very much similar to our previous example in the beginning. This is the NFA. So the same NFAs we are taking again. So 1 1 1 1 0, and this is our acceptance states Q4. So again you have to now we have to take the transition, we have to draw the transition table, but now with a different It is same, but with a different, you can say, concept that you have studied in your FAs actually. So after looking over this diagram, you have to draw this transition table, states, input symbols, and resulting states. It's a very much similar transition table that you have studied in previous lectures. So at Q0, taking input symbol 0. And where I am reaching Q4 at Q0. At Q0, taking input 0, reaching Q4. This is Q0 taking input symbol 1, where I am reaching Q1 and Q2. So Q0 with 1, I am reaching at Q1, and then I am reaching at Q2. So Q1 and Q2 is the pair that is coming here in the resultant states. Now this Q4 is a new thing, so I am going with this Q4. Q4 with 0, Q4 with 1. Q4 with 0, I don't have any edges here, so it is null in both the cases. Now this Q1, Q2. So Q1, Q2 with 0, Q1, Q2 with 1. So Q1, Q2. So you have to check Q1 with 0, and then you have to check Q2 with 0, and then you can end up with some new pair if it is. So Q1 with 0. Q1 with 0, I don't have any edge. Q1 with 0. Q2 with 0. Q2, this one, I don't have any edge. So there is a null here. So Q1, Q2 with 1. Q1, I am reaching at Q0. Q2 with 1, I am reaching at Q3. So Q0, Q3 may be the new pair. So Q0, Q3 may be the new pair. So this is something finished. So Q3, Q3. So you can write these things again like this one. And similarly, this Q0, Q4, I'm not checking now. You can check by yourself. Q0, Q4 is a new pair. So Q0, Q4 with 0 and Q0, Q4 with 1. So Q4 is already handled. Q1, Q2 is already handled. So nothing is remaining here in this resultant states. So this transition table is now ended. And now, after looking over this transition table, you can draw a new diagram. So for example, here Q0 is the state, and with edges 0 and 1, where you are reaching Q4 and Q1, Q2. So Q0 is the state from the transition table, with 0, where you are reaching Q4. So that's why Q4 is mentioned here. And this Q0 with 1, where you are reaching Q1, Q2. So you have to mention Q1, Q2 like here with 1. Okay. So now from Q4 with 0 and 1, I don't have anything. So this null, I can, for example, when in this transition table, when you have nothing in it, you can represent that edge in a state. You can introduce a new state and label it with R, which means it's a rejection state. And for example, here this is nothing, or null, you can say. So you can draw an edge from Q4 with label 0, and you can connect that edge into this nothing state, which is your rejection state actually. So for example, if I draw this rejection state, if this state is nothing state, then from Q0 with 0, I can draw this edge here, this one, Q0, 0, I can draw this to R with Q4 1, with Q4, from Q4 with 1, this is also the depiction of this thing. And from Q1, Q2, 0 edge going to rejection state. Q1, Q2, 0 edge going to rejection state, nothing state. And there's Q1, Q2 with 1, where I'm going Q0, Q3. Q0, Q3. So I can introduce Q0, Q3 here, and with 1, I can represent it with this one. And from Q0, Q3, 0 with 0, where I am reaching Q0, Q4 with 0, Q0, Q4. Q0, Q3, 1, Q1, Q2. Q0, Q3, 1, Q1, Q2, previous ones. And Q0, Q4, 0, Q4. Q0, Q4, 0, Q4. And similarly, Q0, Q4 with 1, Q1, Q2. Q0, Q4 with 1, Q1, Q2. So all edges are now fixed. Maybe this nothing. If there is, if This is the rejection state. And from this rejection state, I cannot draw an edge to these other states because this is rejection state. And if your machine once reaches at this state, you don't have to uh, uh, draw some edge here back to other states, because in this way you are allowing your machine to process string. If those strings are approaching in rejection state, then you are allowing to go back to your legal states, or your accept are states which can help in accepting that state. So you don't have to allow an edge from this state to other states. That's why the loop with 0 1 is here in this state, which means that if at some stage some string will reach at this stage, at this state, it will not go back to other states, because this is the actual meaning, this is the actual sense of this nothing state, this is the actual sense of this rejection states. So so this is basically if this is not the part of your NFA, sorry, now this is not NFA, this is now FA. This is my NFA. This is my NFA. Here I have more, for example, 0, 1, 1, and this one, 3 edges. This is NFA, but this is now my DFA. I am converting that NFA into DFA. So from this one, the input symbol 2, 2 edges, 2 edges, 2 edges, 1 and 2 edges, Q4, this one, 2 input symbols, 2 edges, this one and that one is, and this nothing state, I have to complete it with loop with 2 edges. So this is now FA or DFA, you can say. So this is the example of conversion of an NFA to FA. So if you will make this dotted area rejection state, then this would be the complete example of DFA. If you will ignore it, then it would be an simply an FA. Now another example. So this is now the NFA. It should have maximum how many edges? 2 raised power 2 symbols, 4 state, 2 raised power 4, 16 states in resultant FA. So this is also a formula uh, for your understanding, that you can use this formula to understand that how and what would be the number of the maximum states in the resultant FA. So again, you have to draw the same transition table. You can check this one by yourself, and then you have to draw the states in similar way. uh, you can check this one, the same method. uh, it is for you, it is already solved. And finally, there is a statement of the theorem, there is a statement of some theorem that for any NFA M with 5 tuples accepting some language L, which is a subset of sigma star, there is an FA M1. If we have an NFA M, then there would be an FA M1 with Q1, sigma 1, Q1, A1, delta 1, that also accepts L. So theorem is that if you have an NFA, then there would be, or must be, you can say, an FA for that NFAM, which, and both the NFA and this FA will accept the same languages. This theorem is available in the book. You can read it by yourself. And thank you very much. And now in the next section, I will take the questions from the whole class. Thank you very much.